Hey everyone, and welcome to this explainer. Today, we're uncovering something pretty amazing, the hidden architecture of our everyday lives. Seriously, think of classical mechanics as the invisible source code governing literally everything we experience. From that phone in your hand to the planets orbiting in our solar system, it's all running on the same underlying program. We're going to break down the mechanics of motion and the forces that dictate exactly how our reality operates. And the best part? We're doing it using some beautifully simple principles.
Okay, let's dive into this. We've all heard the famous legend, right? Sir Isaac Newton is just chilling under an apple tree, an apple bonks him on the head, and suddenly, boom, he starts pondering the very nature of motion and gravity. Now, whether that apple actually hit him or just fell nearby, that single, simple moment of curiosity, it sparked an entirely revolutionary theory of motion. Ideas that seemed totally groundbreaking back in the 1600s are now the absolute bedrock of dynamics, the study of forces that affect how objects move.
So, here's our quick roadmap for today. We'll start with the basic rules of motion and momentum, then move chronologically through Newton's three foundational laws, making a quick stop to understand impulse along the way.
All right, Section 1, the invisible rules of motion.
To really grasp how Newton completely changed the world, we first have to understand dynamics. These are the forces affecting objects, whether they're sitting here on Earth or floating out in the vacuum of space. Now, Galileo actually laid some critical groundwork for this. He basically proposed that an object moves at a constant speed when no net force is acting on it. Think about it like this. If you push a heavy book steadily across your desk, the force from your hand is perfectly balancing out this invisible force of friction that's pushing right back. Your pushing force and the friction are totally equal in magnitude, but they're pointing in opposite directions. So the vector sum of those forces, what we call the net force, is exactly zero. This perfectly balanced, steady motion is the exact foundation Newton built his entire empire on.
Moving on to Section 2, momentum, or mass in motion.
Before we actually get into Newton's famous laws, we really need to understand linear momentum. It's basically a simple product of an object's mass and its velocity. And this brilliantly illustrates exactly how mass and speed interact. Picture a massive 20,000 kilogram truck cruising along at a modest 6 meters per second. The math tells us its momentum is a huge 120,000 kilogram meters per second. Now compare that to a tiny 45-gram golf ball rolling at 4 meters per second. Even though it's moving pretty well, its mass is just so unbelievably small that its momentum is barely a blip, just 0.18 kilogram meters per second. It is all about that mass in motion.
So let's do a quick mental check to keep those gears turning. What would be the momentum of a 3-kilogram ball moving at 2 meters per second to the right? You just multiply mass by velocity, and you get 6 kilogram meters per second. Simple enough, right? But hey, notice how we specifically said to the right. That is absolutely crucial, because momentum is a vector quantity. Direction absolutely matters here. If that exact same ball was traveling at the exact same speed, but in the opposite direction, its momentum would actually be -6. So remember, direction is just as important as speed.
All right, Section 3, the first law, or as I like to call it, the laziness principle. This first law describes exactly what happens when there's absolutely no external force messing with an object. Like I said, it's basically the universe's ultimate rule of laziness. Newton figured out that a body will just keep doing whatever it's doing, whether that's sitting completely still or moving at a constant speed, unless it's forced to change by some outside force. We usually call this the law of inertia. And fun fact, inertia literally comes from the Latin word for laziness. It's a body's stubborn reluctance to change its state. In physics, an object's mass is quite literally just a measure of its laziness. The heavier it is, the lazier it is, and the harder it's going to be to get it moving or to make it stop.
Now, there are actually 3 distinct types of inertia that we feel every single day. First up is the inertia of rest. Imagine walking up to a mango tree and giving it a really good shake. The branches move right away, but the mango's inertia wants to just hang there at rest, which causes it to snap off and fall. Second, we have the inertia of motion. You know that feeling when you're on a bus and the driver slams on the brakes? Your lower body stops with the bus, but your upper body's inertia wants to keep cruising forward, so you violently lurch ahead. And finally, the inertia of direction. When you're in a car that takes a really sharp left turn, your body wants to keep going in a straight line, making it feel like you're being pushed hard outward to the right.
Because of the very real physical danger of this inertia of motion, we literally have to engineer our vehicles to counteract Newton's first law. It's why seatbelts are designed to physically lock and tighten around us. They have to overcome our body's stubborn reluctance to stop. It's why airbags explosively deploy to safely intercept our forward-moving mass. And it's exactly why modern cars have crumple zones, designed to crush and absorb all that impact energy over time, so our fragile bodies aren't forced to take it all in a split second.
Which brings us perfectly to Section 4, the second law, force and acceleration.
If the first law is all about laziness, the second law tells us exactly how we force these lazy objects to change what they're doing. Now, what's really interesting about this slide is the sheer contrast in scale. Picture a basketball player giving a solid chest pass. The basketball accelerates super fast, right? Now, imagine that exact same player walking up to a stalled, heavy SUV and pushing it with that exact same amount of force. The SUV is barely going to budge, let alone accelerate. This perfectly shows that acceleration is inversely proportional to mass, meaning the bigger the mass, and remember, that means greater laziness, the smaller the acceleration you're going to get from a given push.
So, the real beauty here is that we can boil all these observations down into one perfectly elegant mathematical sentence. F equals ma. Force equals mass times acceleration. It simply means that the rate you change an object's momentum is directly tied to the force you apply to it. Honestly, this famous math equation is just the formal language we use to describe that basketball and SUV analogy we all just intuitively understood.
To really put the scale of F equals ma into perspective, think about stopping a speeding vehicle. Say you have a massive 12,000 kilogram truck and you need it to decelerate from 30 meters per second down to 5 meters per second, all in just 7.5 seconds. That is going to require a monumental amount of force. When you run the numbers, mass times that acceleration, it turns out you need an average braking force of 39,600 newtons. Again, the greater the mass, the harder you have to fight to change its speed.
Let's slide over to Section 5, impulse softening the blow. Impulse is basically the second law's sidekick, and it's all about how we soften the physical blows when momentum changes. Picture catching a really fast-moving cricket ball or baseball. Its momentum has to drop to zero, which means a force has to act against it over a specific amount of time. You can actually take the painful sting right out of that catch by consciously drawing your hands back as the ball lands in them. By just increasing the stopping time, making the catch take a fraction of a second longer, you drastically reduce the average force hitting your hand. It's the exact same physics principle that explains why a long jumper lands in a pit of soft sand instead of solid concrete. The sand stretches out the time it takes to stop, gently reducing the athlete's momentum. So, here's a rhetorical check-in for you. If a 156-gram cricket ball is hurtling at your face at 54 meters per second, how exactly does impulse save your hands when you catch it? Well, impulse is defined as force multiplied by time, which equals the total change in momentum. By drawing your hands back, you're cranking up the time variable in that equation. And because the total change in momentum stays the same, the force variable absolutely has to go down. Physics is literally saving your hands from breaking. Pretty cool, right?
And finally, Section 6, the third law, action and reaction. While the first two laws are mostly dealing with a single object doing its thing, this third law governs what happens when two bodies bump into each other. And it gives us arguably the most famous quote in all of physics. To every action, there is an equal and opposite reaction. All this means is that if body A pushes on body B is going to push back on body A with the exact same amount of force, but in the exact opposite direction. Basically, forces always come in pairs.
Let's move to and see how this builds into quite literally everything we do. Let's do some rapid-fire reactions. When you're swimming, you push the water backward, right? Well, the water reacts by pushing you forward. How about birds? They fly by pushing the air downward and backward, so the air pushes their wings upward and forward. And let's bust a major myth while we're here. Rockets do not push against the ground or the Earth's atmosphere to take off. Nope. A rocket exerts a massive force expelling hot gases out its back, and those gases exert an equal, opposite force pushing the rocket forward. That's exactly why they can maneuver effortlessly in the complete emptiness of space.
You know what? You can literally test this law right now. Seriously, go ahead and push hard against the edge of your desk or your table. You will physically see your skin squish and distort, and you'll feel the pressure building up. That is clear, undeniable proof that a force is pushing back on you. The harder you push the desk, the harder the desk pushes into your hand. We only ever feel forces that are exerted on us.
So when you think you're feeling yourself pushing the desk, what you're actually feeling is the desk fighting back.
As we wrap up this explainer, I want you to take a second and just look around the room you're in. Look at your chair, your computer, your own body sitting there. Gravity is constantly pulling you down, but your chair is pushing right back up with an equal and opposite force. Your inherent laziness, your inertia, is keeping you perfectly at rest until something makes you move. These aren't just dry equations in a textbook. This is the active and visible source code holding your immediate reality together this very second. So, what force are you going to apply next to change your momentum? Thanks for exploring this with us, and keep questioning the mechanics of your world.